So in previous session we talked about binary numbers, right? So how can you convert a decimal number to binary, or in fact to any other base, and how can you convert a binary number to decimal, right? So why are we talking about binary numbers? Obviously because it is very important. Deep down things are in binary. So now let's start with a simple statement like this. This is, as I said, the starter statement, and it has loads of concepts hidden in this very statement itself. So when you do this, you get a storage with name I. This storage is a 4-byte long storage, right? And 10 will be stored here. Now 10 directly as a number is not stored here, decimal number. The binary representation of 10 is eventually stored, right? So what is the binary representation of 10? 1010, right? So that means you have 32-bit space here. I'll write it like this. So I have 32-bit space here and I want to store binary representation of 10. Now binary representation of 10 actually requires only 4 bits, right? So what are we going to store in remaining 28 bits? So all those 28 bits are going to be 0. So first 28 bits are going to be 0, and then we will have 1010 in last 4 bits. So this is how a binary number is going to, or 10 as a binary number is going to be stored in memory. Okay, so this was very specific. We were talking only about 10. Now let's generalize. Let's generalize and try to reach to a conclusion that if I have 32 bits in total, what is the range of numbers that I can store in those 32 bits? That means what will be the smallest number that I can store here, or what will be the largest number that I can store here. So we are trying to reach out to this A and B range. A being the smallest number, B being the largest number, and considering the fact that in integers we can store negative numbers as well. So that means you have negative numbers in picture as well. So what is the smallest negative number and what is the largest positive number that you can eventually store into a range? Now, to reach to a conclusion for 32 bits, we will start with a small case of 4 bits. So let's say I have only 4 bits and I want to figure out what can be the possible range of numbers that I can store in these 4 bits. So to do that, I'll even break down to a simpler case. Let's say for now, I am going to store all positive numbers, 0 and all positive numbers. So if I have these 4 bits, what do you think is the smallest number that you can store? So the smallest number that you can store is fill all these bits with 0. 0 is the smallest number that you can store. What will be the largest positive number that you can store? The maximum of 0 and 1 is 1. Put the best digit out there in all 4 bits, right? So all 4 bits being 1. That means with 4 bits in hand, my range actually goes from 0 to 15. Assuming with a big assumption that I'm only storing all positive numbers in these 4 bits, right? So if there are 4 bits, the range is this. 2 to the power 4 is 16, minus 1 is 15. So that means had there been n bits, the range would have been 0 to 2 to the power of n minus 1. But this is with a bit big, I should say, disclaimer that you are trying to store only positive numbers. Practically, when you have 4 bits, maybe these 4 bits, you would want to store both positive and negative numbers in these 4 bits. Right? So now let's talk about the scenario. If we try to store negative numbers, what all is going to change? So first of all, talking about only decimal representation, plus 10 minus 10. If I have this, then the differentiator in these two representations is sign. Right? So that means you are using sign as an indicator to indicate whether it's a positive number or it's a negative number. So that actually means if I have these 4 bits and I'm trying to store a number, let's say that number is 2, plus 2 minus 2. And I have these 4 bits only to store that number. First of all, binary representation of 2 is 10, right? So that means 10. So if I want to store plus 2, I should have a sign indicator. If I want to store minus 2, I should have a sign indicator as well. So let's come up with a proposal 1. This is just a proposal. So proposal 1 says what you are supposed to do is use the first bit as sign bit. Plus 10 minus 10 or plus 2 minus 2, right? The number is same. The only difference is sign. So store the same number here and here as well. And the first bit will be used to represent the sign. 1 for negative, 0 for positive. That means if this bit is on, it is a negative number. If this bit is off, this will be a positive number. So that means if I want to store minus 2, the first bit will be the sign bit and this bit is going to be 1. If I have to store plus 2, the first bit will be the sign bit and this bit will be 0. What about remaining bits in between? They all will be filled with 0. So that means the proposal 1 says use the first bit as sign bit. If sign bit is on, it's a negative number. If sign bit is off, it's a positive number. And whatever is the binary representation of that number, store that binary representation in remaining bits. So remaining bits, 2 is represented as 1, 0, right? So same binary representation in both scenarios. This is plus 2 and minus 2 case, right? So this is how you can store, right? I hope this makes sense. Now tell me, if I have 4 bits, what is the possible range of numbers that you can store? What is the largest positive number and what is the smallest number, right? So the largest positive number, and since it is a positive number, sign bit should be 0. And it should be largest, so all remaining bits should be filled with 1, right? And because I'm talking about the smallest number now, so largest positive when negative will be the smallest negative, right? So that means the sign bit should be 1 and all other bits should be set to maximum. So that means in this case, the range eventually will be, if I read this number, this is going to be 1, 1 means negative, remaining 3 bits represent 7, so this is going to be minus 7, positive number will be plus 7. So that means if I store my number this way, my range is going to be minus 7 to plus 7. Right? So I hope this makes sense. What proposal do we have? The proposal we have is just keep the first bit as sign bit, and whatever is the binary representation of the number, just store that as it is. Right? Now there is one flaw with this idea, or one issue with this idea. Now the problem with this idea is, let's say I am storing a number like this. What exactly it is? How will you read a number? So wherever you have to read a number, start reading that number by sign bit. Sign bit says 0, that means it's a positive number. Now how much positive the number is, that is stored in the remaining bits. So here, if you try to store all zeros, that means the number is positive 0. What about this? Read the sign bit. Sign bit says it's negative. Remaining bit says it's 0. That means the number is minus 0. So that actually means in this representation, you have two, or I should say in this proposal, you have two representations of zeros. There is a plus 0, there is a minus 0 as well. And that will cause confusion. So practically in system, negative numbers are actually not stored this way. So this was just a proposal to get some understanding on how can we actually use the bits we have to store negative numbers, right? So how is, I should say, the numbers stored then eventually? So there is a slight change in which, slight change in manner in which we are going to store numbers. For positive numbers, there is no change. If you have a plus 2 and you have 4 bits, sign bit should be 0. Store the representation of 2 in the remaining bits as it is. So positive numbers, in case of positive number, there is no actual change. But in case of negative numbers, there is actually a change. So let's now discuss how can we store negative numbers and talk about minus 2 precisely. So for now, let's just write 2. If you have to store 2 in 4 bits, how are you going to write it? So 2 in 4 bits will be somewhat like this. But this is not 2, this is minus of 2. So if you have to store negative numbers are actually stored in their 2's complement form. Now what exactly is 2's complement form? So 2's complement is 1's complement plus 1. So that means if you have to store minus 2, you have to calculate 2's complement of minus 2. How can you calculate 2's complement? So first calculate 1's complement. Calculating 1's complement is pretty easy. If you have to calculate 1's complement, all you have to do is just reverse all bits or toggle all bits. If it is 0, put it 1. If it is 0, make it 1. If it is 1, make it 0. If it is 0, make it 1. So this is 1's complement. Now add 1 to that 1's complement. So 1 plus 1 is 2. Now 2 is not a digit in binary, right? So 2 is 1, 0. So we'll keep 0 here and put 1 as carry. I hope you remember adding decimal numbers, right? So if we have 9 plus 1, what we do is 0 here, 1 carry. Similarly, if we have 1 plus 1, that is 2. 0 here, 1 carry. 1 plus 0 is 1. This is what we have. So this is the final number we have. So that means if you have to store minus 2 in system, eventually it is going to be stored this way, in 2's complement form. Why are we even talking about 2's complement form? Because 2's complement form is the actual form in which binary numbers are being stored in system. This is how they are stored in system deep down. So I hope that this is clear. In fact, let's take another example. Let's say I have to store minus 1. How do you think minus 1 is going to be stored? Now, because this is a negative number, you will have to store it in its 2's complement form, right? So, how are you going to store it in its 2's complement form? So, just write down the binary representation of 1. This is the binary representation of 1. Take 1's complement. 1's complement is invert all bits. Add 1 to 1's complement. And that is it. So, if you have to store minus 1 now, minus 1 will be stored this way in 2's complement form. Right? So, this was converting a number to 2's complement form. Let's do vice versa. Vice versa would mean that I am giving you a number like this maybe, and you want to read that what exactly this value is. So, whenever you have a binary number, start reading it from its sign bit. Now, if sign bit says 1, that means it's a negative number. And because this is a negative number, this is not stored directly, this is stored in its 2's complement form. That means to get back the original form, get back the original number, we will have to take 2's complement again. So, quickly take a 2's complement of this number. So, if this is the number we have, so take 1's complement first. This will be the 1's complement. Add 1 to 1's complement. So, adding 1 to 1's complement will make it this. Just convert this to decimal. This is 2. Sign was negative initially, so this is minus 2. So, that actually means now this is the representation of minus 2. So, I hope now you have some clarity on 2's complement form. If you still feel you have some confusion, just pause the video, pause the session, write down, try writing the conversion alongside yourself. Now, let me clear this. So, let's get back to the original problem. The original problem with which, or the original motivation with which we started was, in proposal 1, we had two representation of zeros, plus 0 and minus 0. And this was not what we wanted, right? So, which is why we talked about 2's complement form. So, if you have 0 here in 2's complement form like this is still going to be 0. But you have 0 like this is no more minus 0. Then what exactly is this? Let's read that. So, if you have to read what this number is, follow the same process. First, read the sign bit. This is the sign bit, that means it's going to be a negative number ultimately. Now, if this is a negative number, it will be stored in its 2's complement form. So, take 2's complement to get the original number. Now, 2's complement will mean toggle everything and then add 1. So, if we have to add 1, 1 plus 1 is 2, 0, 1 carry, 1 plus 1, 2, 0, 1 carry, 0, 1 carry, and this. So, this is the final number you have. Now, what is this number? So, 1, 2, 4, 8. If you convert it to decimal, this is 8. So, that means this number is now minus 8. So, 2's complement form, in 2's complement form, 1, 0, 0, 0 is actually minus 8. In the original proposal 1, which is not the actual proposal, this was minus 0. So, we were wasting this representation and now we are utilizing it. That means in case you have 4 bits, the range of number is minus 8 to plus 7. Plus 7 will be stored this way, 1, 1, 1. Right? So, what if you have n bits? So, in case of n bits, the range of number will be minus 2 to the power of n minus 1 to 2 to the power of n minus 1 minus 1. Why is this n minus 1? Because out of n bits, 1 bit is sign bit. So, to store number, you have n minus 1 bits only, right? So, which is why you have n minus 1 over here. And what is the possible range? So, possible range is this. So, this is something which you should be clear. So, in case of integers, if I have, I'll use this space. So, in case of integers, you have 4 bytes. And 4 bytes means 32 bits, then the range of numbers is going to be minus 2 to the power 31 to 2 to the power of 31 minus 1. Right? So, in case of short, you have 2 bytes, right? So, what is this range? What this range will be? So, this range will be minus 2 to the power 15 to 2 to the power of 15 minus 1. Because it's 2 bytes, that means 16 bits. So, this is how it is going to be. Right? So, I hope now you have clarity how numbers are stored, what is the smallest value, what is the largest value, how 2's complement is calculated. In case there is slight confusion, even just go through the session again, and I hope that should clear things for you. Thank you.